Hello everyone, welcome to our session for today. So our topic is all about introduction to dynamics. Actually, we had already discussed about 90% of the contents of this lecture, but as a sort of review and at the same time to introduce to you the other concept that was not included in the previous session. Okay, so these are the topics: history and modern applications, basic concepts, Newton's laws, units, gravitation, dimensions, and solving problems in dynamics. Okay, so about history and modern applications. So we know that dynamics is the branch of mechanics which deals with the motion of bodies under the action of forces and usually follows after statics. Dynamics has two distinct parts. We have the kinematics, which deals with the study of motion without reference to the forces which cause motion, and kinetics, that relates the action of forces on bodies to their resulting motion. Dynamics is a relatively recent subject compared to statics. So an understanding of dynamics is essential in numerous fields including robotics, automatic control systems, design of rockets and missiles, spacecraft and transportation vehicles, machinery of all types, examples, turbines, pumps, reciprocating engines, machine tools, etc. Then we have here some definitions which we also had discussed before, just a sort of review. So we have what we call space. So when we speak of space, that is the geometric region occupied by a body. And inertial reference frame, a set of rectangular axes assumed to have no translation or rotation in space. It is also referred to as an astronomical frame of reference and is the basic frame of reference for the laws of Newtonian mechanics. Then we have time. Time is a measure of succession of events considered absolute in Newtonian mechanics. Mass is a measure of the inertia or resistance to change in motion of a body. It is also a measure of the quantity of matter in a body. Force is the vector action of one body on another. So it has magnitude and direction. Then particle is a body of negligible dimensions. Then we have rigid body. Rigid body is a body whose changes in shape are negligible compared with the whole dimensions of the body or with the changes in position of the body as a whole. Vector, quantity with magnitude and a direction. Example, force, velocity, acceleration, torque, etc. Then we have scalar. Scalar is a quantity with only a magnitude. For example, time, volume, density, energy, mass, etc. Then here comes the three laws of Newton's law of motion. So law number one, a particle remains at rest or continues to move with uniform velocity in a straight line with a constant speed if there is no unbalanced force acting on it. Okay, so it continues to remain at rest for as long as there is no unbalanced force acting on it. Then the second law of Newton's motion, so the acceleration of a particle is proportional to the vector sum of forces acting on it and is in the direction of the vector sum. Okay, then the third law, the forces of action and reaction between interacting bodies are equal. So they are equal in magnitude but opposite in direction. And collinear, it means that they lie on the same line. Now we have here comments about Newton's law or Newton's laws. So the laws have been verified by countless physical measurements. And the first two laws hold for absolute or inertial reference frames. The second law forms the basis for most analysis in dynamics and takes the common form of F equal to the product of the mass and the acceleration for a particle, where F is the resultant force which acts on the particle, and m is the mass of the particle, a is the acceleration of the particle. So the first law is a consequence of the second law and is the primary subject of the study in statics. The third law is the principle of action and reaction from statics. So we have here the units of measurements. So fundamental quantities of mechanics and their units. So we have here the quantity, that is the mass, length, time, and force. And these are the symbols. For mass, we have the symbol m, length, L, time, T, force, F. For the SI units, so here comes the base units, the kilogram, meter, and second. And the Newton is the derived units or unit. Then these are the symbols for kilogram, kg, meter, m, second, s, Newton, capital N. For the US customary units, so we have here the base units, that is the foot, second, and pound. The slug is the derived units. And these are the symbols. For slug, there is no symbol for slug, so you have to use the whole word slug or slugs. And then we have ft for foot, then second, sec for second, and lb for pound. So the SI system is absolute. SI system is absolute, so you have to remember this one. So SI system is absolute. So the reason is that the standard for the base unit of mass, the kilogram, is independent of the gravitational attraction. So remember this, independent of the gravitational attraction of the Earth. So we have here the base units, kilogram, kg, meter, m, second, s. And the derived units is the Newton, capital letter N, the symbol. Force units, so Newton is equal to kilogram meter per second squared. So that is equivalent for Newton. 1 Newton is 1 kilogram meter per second squared. For US customary units, so the US customary system is gravitational. So dependent on the gravity. So gravitational because the standard of the base unit of force, which is the pound, requires the presence of the gravitational field of the Earth. And here comes the base units, the pound, foot, second. And these are the symbols, LB, FT, SEC. Then the drive unit is the slug. So the symbol used is none. So we usually use the whole word slug or slugs. Then we have mass unit, slug equal to pound second squared per foot. Okay. Now the law of gravitation have this mathematical expression given in this expression. F is equal to G, capital G, times the product of M1 and M2, where M1 is the mass of the particle 1, M2 is the mass of the particle 2. So we have to refer it to this illustration here, class. All right, and then R is the distance between the center of the two particles, or the center of the particles. Okay, so for M1 the center is here, for M2 the center is here. So the measurement, which is R, so that is the R that is being used in this formula, where F is the mutual force of attraction between two particles, and G is the universal constant known as the constant of gravitation. M1 and M2, the masses of the two particles. R is the distance between the centers of the particles. Then we have here constant of gravitation, G. So for SI units, G is equal to 6.673 times 10 to the minus 11. So the unit here is in terms of meter cube or cubic meter per kilogram second squared. For US units, so G is equal to 3.439 times 10 to the minus 8 feet to the fourth power per pound second to the fourth power. Okay, so remember this formula, class. This is one of the important formulas, a basic formula that in physics that we need to understand and remember. There are a lot of problems where you are required to use this formula, especially if the problem involves Earth or objects like the moon and so on and so forth. Then effect of altitude. So if you look at this illustration here, we have the rocket or something, a particle moving horizontally. We have here the Earth. Then we have R is the radius of the Earth. We have here the height of the particle flying above the Earth. So the acceleration of gravity at altitude h is given by this expression, G equal to G sub 0 times R squared divided by the quantity R plus h raised to power 2, where G sub 0 is the absolute acceleration. Alright, so remember this, absolute acceleration of gravity at sea level. That is equal to 9.825 meter per second squared, or that is 32.23 feet per second squared. So absolute, you have to distinguish how to distinguish this acceleration and the other type of acceleration. So at sea level, so these are the absolute acceleration of gravity. H is the altitude above the surface of the Earth. R is the radius of the Earth. That is 6,371 kilometers or 3,959 miles. This equation can be used to determine the acceleration of gravity at altitude above other celestial bodies, example, the moon, Jupiter, the sun, etc. Then we have here effect of a rotating Earth. So we know that the Earth is revolving around the sun, and the Earth itself is rotating, at its center. So while it's rotating around the sun, it's also revolving. All right. So 1980 International Gravity Formula. So we're given this. So that was around or more than, or it's already 40 years. So G here is given in this equation as 9.780327 times 1 plus 0.005279 sine squared gamma plus 0.00023 sine to the fourth power of gamma plus and so on and so forth, where gamma is the latitude. Okay, so if you look at this illustration here, gamma is the horizontal part of this coordinate system, and G is expressed in meter per second squared. Now for the non-rotating Earth variations, you just simply add to this formula. You just simply add 3.382 times 10 to the minus 2 cosine squared gamma meter per second squared. So you just add this component to this given equation. So this removes the effect of rotation. So when you plot these equations, class, you will see these curves here. So the curve above, so this is the curve for the non-rotating, all right? And this is for the relative to the rotating Earth international gravity formula, this graph below. Okay, so the vertical component here, so this is the acceleration. Okay, so the acceleration that is in g meter per second squared. All right, so this was the 1980 international gravity formula. So perhaps this time it's already changed. Then standard value of g. So relative to a rotating Earth at sea level and at a latitude of 45 degrees. So for the SI units, our G is equal to 9.80665 meter per second squared. And for the US units, G is equal to 3 or 32.1740 feet per second squared. So values for most problems in mechanics that we need to memorize, okay, and know where these values were taken from. So for the SI units, G is equal to 9.81 meter per second squared. For the US units, G is equal to 32.2 feet per second squared. So in our calculations of the problems that we will be solving later on, we have to use mostly of these constant values for acceleration. Then we have what we call apparent weight. So denoted by the letter capital W. So this is equivalent to the product of mass and the acceleration, gravitational acceleration. So SI problems. So this is the SI problems. Mass is always in kilograms. Okay, so take note of that for SI problems. Mass M is always in kilograms. So you have, if you're given in terms of grams or other units, you have to convert that into kilograms. And is almost always provided in the book. Acceleration of gravity or gravitational acceleration, G is equal to 9.81 meter per second squared unless stated otherwise. And the weight W is in Newton. The symbol used is capital letter N. Kilogram, the symbol used is kg. So take note that kilogram is not a force. Okay? It's not a force. For US problems, mass M is always in slugs, right? And is almost never provided in the book. So acceleration of gravity, G, is equal to 32.2 feet per second squared unless stated otherwise. So the weight W is in pounds. The symbol is lb and is usually what you are provided. So pound lb is not a mass as well. Okay? I hope it's clear, class. Now for the dimensions. So dimension is a quantity that can be expressed in a number of different units. Example, length. So the length could be expressed in terms of millimeter, mm, or meter, m, feet or foot, ft, miles, mi, etc. So principle of dimensional homogeneity. All physical relations must be dimensionally homogeneous within an equation. So useful for checking the dimension correctness of a derived physical relation. So this is necessary condition for correctness, but not a sufficient condition. Now in solving problems in dynamics, so we have here the following procedure that we need to follow, in order for us to be able to solve it. So we have what we call the dual thought process. So dual thought process in dynamics. Think about the physical situation and the corresponding mathematical description. Then make appropriate assumptions and approximations. Then use graphics. So representing a problem geometrically helps us with its physical interpretation. This is especially true for two-dimensional problems in kinematics. Graphical solutions can often be obtained more readily than with a direct mathematical solution. Charts and graphs are valuable aid for representing results. So formulating problems and obtaining solutions. So number one, formulate the problem, state the given data, state the desired result, state your assumptions and approximations. Now in developing the solution, so we need to draw any diagram and include coordinates which are appropriate for the problems at hand. State the governing principles to be applied to your solution and make your calculations. Ensure that your calculations are consistent with accuracy justified by the data. And be sure that you have used consistent units throughout your calculations. Ensure that your answers are reasonably or reasonable in terms of magnitudes, directions, common sense, etc. Then draw conclusions. Then the free body diagram. So isolation of a body from all other interacting bodies. So develop fully in statics, single most important step in kinematic problems. So the free body diagram. Then numerical values versus symbols. So symbolic solutions advantages. It helps to focus attention on the connection between the physical situation and its related mathematical description. Can be used repeatedly for obtaining answers to the same type or problem but having different units or numerical values. It enables dimensional checks at every steps to ensure dimensional homogeneity. Then for the solution methods, we have 1. Obtain mathematical solutions by hand using either algebraic symbols or numerical values. We can solve most problems in this way. Then obtain graphical solution for certain problems and solve problems by computer. So this is useful when a large number of equations must be solved, when a parameter variations must be studied, or when an intractable equation must be solved. So computer is very important for that kind of problem. Okay, so let us apply this concept in solving this problem here. So we have here the problem statement. A space shuttle payload a space shuttle payload module weighs 100 pounds when resting on the surface of the Earth at a latitude of 45 degrees north. A. Determine the mass of the module in both slugs and kilograms and its surface level weight in newtons. Now, suppose the module is taken to an altitude of 200 miles above the surface of the Earth and released there with no velocity relative to the center of the Earth. Determine its weight under these conditions in both pounds and newtons. And C. Finally, suppose the module is fixed inside the cargo bay of a space shuttle. So the shuttle is in a circular orbit at an altitude of 200 miles above the surface of the Earth. Determine the weight of the module in both pounds and newtons under these conditions. For the surface level value of the acceleration of gravity relative to a rotating Earth, use g equal to 32.1740 feet per second squared. That is equivalent to 9.806665 meter per second squared. For the absolute value relative to a non-rotating Earth, use g equal to 32.234 feet per second squared or 9.825 meter per second squared. Round off all answers using the rules of this textbook. Okay, so here's the illustration, class. So there's a scenario where the weight is lying on the surface of the earth or resting. And the other scenario is that it's above the earth, 200 miles above the earth, that is not moving. And the other one is when it's inside the shuttle, space shuttle, revolving around the earth at 200 miles from the surface of the earth. Okay, now for part A. So mass of the module. So the mass of the module can be calculated using the formula of the weight. The weight, which is equal to the product of the mass and the gravitational acceleration. So from that equation, we can solve for m. M equal to W divided by G. So substituting the values, okay, so our W given the problem, that is 100 pounds, and G, so we use this G, that is 32.1740 feet per second, and it gives us 3.11 slugs. So this is our answer for letter A. Now we can use the conversion or unit conversion in the table. Table D5 in our previous slides, where M equal to 100 pounds. So multiply this, convert this into uh, in terms of kilograms. So pounds change to kilogram. So 100 pounds meter. So this is equivalent to 0.45359 kilogram per 1 pound meter. Or this is equivalent to 45.4 kilograms. So this is the mass in terms of kilogram. Okay, the other one is in terms of slugs. Okay, so alternative approach for solving the kilogram. So from the table of conversion factors in table D/5 of appendix D, so we see that 1 pound is equal to 4.4482 newtons. Thus the weight of the module in newton is, so using the conversion, we have weight is 100 pounds times 4.4482 newton per 1 pound equal to 445 newton. Alright, so we got the answer here, 445. So if you compare that, okay, so that is 445. So we got that in terms of newton. Now to convert this into kilogram, so we have a conversion that we have to use the mass, no, from this formula. So here we get the weight first using the conversion. So you solve for the weight, then after that use the formula in finding the weight. Okay, so that is taken from this formula here. Weight is equal to the product of the mass and the gravitational acceleration. So from there we can solve for mass, substituting the result here. Okay, and then G is 9.80665 meter per second squared. So it gives us 45.4 kilograms. So it gives us the similar result as we had done in the previous slide. Okay, so we have to take note, no, similar to our note number 1. We have here our calculator indicates a result of 3.108099 slugs. So it refers to this result class. Okay, using the rules of significant figures display used in this textbook, so we round the written result to 3 significant figures. So this is the 3 significant figures class. Okay, had the numerical result begun with a digit 1, so we would have rounded the displayed answer to the 4 significant figures. Alright, then the second note is that a good practice with unit conversion is to multiply by a factor such as this factor class, which has a value of 1. Okay, which has a value of 1. Because the numerator and the denominator are equivalent, be sure that cancellation of the units leaves the units desired. Here, the units of pound cancel, leaving the desired units of n. Okay, and then note number 3. Note that there are we are using previously calculated result 445 Newton. So we must be sure that when a calculated number is needed in subsequent calculation, it is obtained in a calculator to its full accuracy. Okay, so it means that you have to write down all the numbers after this 2 here. Okay, so that your value will be much accurate. So the resulting value that you will obtain using this value, for example, will be more accurate. So if necessary, numbers must be stored in a calculator, uh, cal calculator storage register, and then brought out of the register when needed. So we must not merely punch 445 into our calculator and proceed to divide by this number. Otherwise, the result is not accurate. So this practice will result in loss of numerical accuracy. Some individuals like to place a small indication of the storage register used in the right margin of the work paper directly beside the number stored. Okay, so you have to mind of all these notes, class. These are very important. Now for B, so weight of the module at 200 miles. So now the module is already above the surface of the Earth at 200 miles. So G is equal to G sub 0 times R squared divided by R plus H quantity. So this denominator here, sum of this denominator raised to 2. So the weight at an altitude of 200 miles is then calculated. So we have weight with the subscript H here, meaning there's an altitude above the ground, above the surface of the Earth, equal to M times GH. So we have calculated already the mass, that is 3.11 slugs. So using this and then multiplied by the gravitational acceleration, 29.2, and then we got this 90.8 pounds. So that would be our answer. We now convert the weight with the subscript H to units of newtons. So use this result and then convert it using this conversion factor, and it gives us 404 newtons. Okay. As an alternative solution to part B, we may use Newton's universal law of gravitation. So in US units, so we use this F equal to G m1 m2 over r squared. So our WH or W sub H equal to, okay, so that is G times M subscript E times M divided by R plus H, then everything in the denominator raised to power 2. Okay, and then substituting our G here as given the problem, this one also given, and this one is calculated. Okay, so this is given, and the next number M mass is given. This is calculated, and divided by R. Okay, so we have here our R. So 359, that is the in terms of miles, because we have the unit slugs here. So we have in terms of miles. Okay, then we convert this one because our unit here in terms of feet, no, our gravitational force in terms of feet per second squared. So you have to express this also. You convert miles into feet. So 1 mile is 5,280 feet. Okay, and then when you do the calculations here using your calculator, we get this result. Okay, so we got the same result as here. All right. Now for C, so weight of the module in motion at 200 miles. So this time the module is already moving, no, because it's inside the shuttle or the spacecraft. So the weight of the gravitational force of attraction does not depend on the motion of the object. So the answer for part C are just the same as those for part B. So that is also 90.8 pounds or 404 Newton. Okay, so that's the reason, class. The weight of the gravitational force of attraction does not depend on the motion of the object. That's why the result of part B is just the same for part C. Okay, so I hope you're able to understand, you're able to apply what you have understood from the concept that we just discussed. Okay, so thank you very much and hope to see you again in our next video uh, that will be uploaded soon. See you again next time. Bye.